Hello, good evening, everyone. I hope you can hear me all right.
Yes, good evening, ma'am.
All right, good evening. Okay, I have shared my screen and there we go. All right. So, welcome to the fifth live session of the course Essentials of Data Science with R Software, Probability and Statistical Inference. And just some housekeeping notes. Um, So there are three sessions, Fridays, Saturdays, and Tuesdays. The session for this Saturday, which is supposed to be tomorrow, has been postponed to Sunday. So in case any of you have anything to ask for the Saturday session, you can join on Sunday instead. But again, these sessions, they are roughly going to cover similar things. So attending any one of them should suffice, and anything we discussed in any of these sessions is going to be uploaded to YouTube and to Google Drive. There will be individual links for each of them. There's a Google Sheet, the link to which is available on the NPTEL course page. You can access that for the problem solving session, and then you can access any of the videos or the reading material. And do make use of the discussion forum in case there's any question or anything in the lecture videos that you get stuck at. Okay. And so for the one on Fridays, which I'm taking, four sessions have been done. So we're like one third through this course. Um, we can begin with the fifth session now. Again, if you have any questions, any doubt from what was done until now, if you have any suggestions, let me know. And again, do try to make this interactive. I'll start off by discussing what was discussed in week 5. We would have some slides, and this would be followed by also some R codes. And then we'll get on to some questions. I have about 6 or 7 questions that would give you an idea of the type of questions that are being asked for this week's assignment also. So there definitely it should be more interactive. We'll solve the questions together and we'll see that. And finally, at the end, we will take a look at the solutions for the last week's assignment. All right. Okay. Anything that any of you want to talk about, or should I start with this week's discussion? If there's nothing, then I'll just start. All right. So from the last week, we had seen that there is something known as an expectation. And so think of this in terms of, so if you um, toss, or let's say if you roll a dice, so you can get numbers 1, 2, 3, 4, 5, 6, right? Now, let's say now you know that the dice is unbiased, okay? So you can get 1, you can get 2, 3, 4, 5, 6 with an equal probability. Now, sort of, since the probability is the same, the expected value is going to be an average of those 6 numbers, right? Um, because each of them have the same probability. Now, instead, let's say if the higher numbers had a higher chance of occurring, so think of this as if you're rolling that dice 100 times, you'll get those higher numbers almost double as frequently as you will get the smaller numbers. So let's say 1, 2, 3 have a lower frequency, 4, 5, 6 is going to have they're going to have a higher frequency. So that mean is going to get shifted towards the higher numbers. So in case you are familiar with the concept of a weighted average, right? It's pretty much the same thing, right? So the expectation of a random variable x, it means it is basically going to be a product of the value and its corresponding frequency, or rather in this case, the probability. So this one, so again, the expectation can be there for a discrete random variable or a continuous random variable. For continuous random variable, probability of a point is not relevant, right? If you remember what we had seen, just give me a second. So if you remember the probability mass function and the probability distribution function of a continuous variable. So let's say for a continuous random variable, here you have fx and here this is going to be your x, right? So let's say the plot looks something like this. So the area of the y-axis is not the probability. It is the probability density function. But the area is what is going to give you a probability. And if you are calculating if you are interested in just a value of x, let's say whatever x is equal to 2, then in that case, that area that you're going to be, it's not going to be an area, it's just going to be a single line. And area of a single line is 0. So probability at a value does not make sense. The probability at a certain value is going to be 0. On the other hand, for a uh, discrete random variable, this here directly is x. So for this value, you have a certain value. For another value, you're going to have something else. And this is how it's going to be. So the y-axis is actually that probability, right? So this is also reflected in all the formulas that we'll be seeing now and later. So the expectation of the random variable when it's a discrete random variable is going to be product of that value into the corresponding probability, and you sum that up. For example, the dice case that we took. And when it's a continuous variable, you're going to multiply the random variable with its probability density function, and you're going to integrate it over the range of all the values that it takes. And expectation of x. Now, it depends on what you call x. In my case, let's say I'm talking the sum, or let's say when you've rolled one dice, the number on the top face is what is going to be a random variable. So that becomes x. Let's say, but instead I'm going to define my x as x square. I am interested in the square of the face on the top. But it's still going to be the same thing, right? It's when it's one, so it's not going to be complicated. When the face was 1, the square is 1. When the face is 2, the square is 2. So if it's instead of writing 1, 2, 3, 4, 5, 6, I have written 1, 4, 9, 16, 25, and 36. But it's still the same thing. It's just different numbers, but the funda stays the same, right? It's still as discrete as it was. So in that case, so when you're finding the expectation of not the random variable directly, but some different form or a different function, a different polynomial, anything else which comes from that random variable, it's still going to be a very similar format, right? So you multiply that function, the output of that function, by the PDF and integrate it. And in this case, you're multiplying the probabilities with the corresponding values of that function, right? So it's pretty straightforward. Now, there were a few additional things which were introduced last week, and we are going to take that a little forward in this week, right? So when you're talking about these functions, if the function is of the form that random variable to some power, right? So if this is what you define as your function, and when you find the expectation value of that function, you're just replacing gx with x to the power r, then this becomes the rth moment of x about 0. And this is how it's denoted. It's denoted as mu. The rth power becomes the subscript. And since it's about 0, it's sort of has this apostrophe or a quote next to it. Instead, when there is this form, when it's x minus a and whole to the power r, so basically, in first case, the a was 0. So in that case, it's going to be r rth moment of x about a. In this case, it was the rth moment of x about 0. So it's of this form, right? So this is the general form. And then specifically a being 0, you can call it the rth moment. Now we look at some special cases within this format, okay? So we saw this thing, right? When gx is x to the power r. Now this is actually called the raw moment, the one we saw here, right? It's the same thing. I've just written it in a new slide. It's called the raw moment, right? Again, these calculations of moment that we'll see today, they can be done for both continuous as well as discrete variables. It's slightly simpler to write for discrete variables, and that is what was discussed in the lectures. That's also what I am writing here, but they also apply for continuous random variables, okay? So now if you see what is going to be the format. So if you remember, the format was the function multiplied by the corresponding probability, right? This format. And now you know, when you're talking about a discrete random variable, right? So let's say the probability was of this form. It was a uniform probability distribution, as we're going to see ahead in the course. So if that is what the format is, that probability pi is going to be 1 by n, where n is the number of observations, number of options, number of outcomes. So that becomes a constant, right? So it can just come out of the summation. And this is what your function was, right? Xi, x to the power r. We will see these cases in just 1 minute. So this was the raw moment. When it's about 0, you call it the raw moment. When it's about A, it does not have a name, but when that A is specifically equal to mu, which is the mean, we'll see. So another notation of mu is x bar. And I'm just going to introduce that to you in a couple of minutes. But that expectation, the original expectation that was there, that's called the central moment. Okay. So when A is equal to 0, it's the raw moment. When A is equal to mu, it's the central moment. Don't get confused. All right. Okay. So this is what the format is going to be. It's going to be looking similar. Now, now the only variable, so we had two variables in this, right? One was R and one was A, right? So we have seen A, right? So this is the case when A is equal to 0. And this is the case when A is equal to mu. So A0 is raw moment, A mu is central moment. Now the other variable, which is R, so there are some special cases. Now see, when R is going to be 0, so again, this is going to be 1, right? So you're summing 1 n times, that becomes n. So n by n, that is equal to 1. So it's a constant value. When R is equal to 1, it's nothing but your actual summation of x itself, right? So that becomes mu. If you solve this out, it's going to be summation of x divided by n, which is the average, right? Then in case of the central moment, you can have a few more cases. We'll start off with 0 and 1. So when R is 0, if you solve this, so again, it's going to be 1. R is equal to 0. And then you sum this thing up. This should be 1, I think.
Yes, ma'am. Mu
This should
equals to
be
1. 1.
right? Yeah.
Yes.
I don't know why I've written help here. Oh, I think it's just copy pasting something else. Ignore. Okay, fine. Thanks for the confirmation. Yeah. And when R is equal to 1, so then you will see, so this power becomes 1. So so we have not explicitly talked about this in this course, but this format where what you do is you do x minus the mu, and then when you divide it by n, that's actually going to give you the variance, right? We'll see this a little ahead in the course. That becomes the variance. And furthermore, when R can be 2 or it can be 3, it can be 4, then these other values of mu, this should actually be in the
Ma'am,
subfield.
I think in when R equals to 1, then mu equals to 0. 0 here.
Really? This one?
Yes, ma'am. For the
Oh, correct. You're right. Okay, I think I've missed
yes.
something here. Okay, fine. So let me just show it to you so that it's clear
Mm.
to everybody else. So yeah, so when it's going to be 1 by n. So now what is going to happen? Let's say you had these 5 observations, 0, 1, 2, 3, 4. Right? Now, if you take a mean of them, or x bar, or which is mean, that's going to be 2. Right? 1 plus 4, 5,
Ma'am,
5.
whole row, I think whole row is incorrect. Because when R equals to 2, then mu from here the mu started, and when r equals to 3, then is skewness is started, and r equals to 4, then kurtosis is started. I think that.
So actually, if you see for skewness and kurtosis, mu3 and mu2 both are being used, right? For like skewness, kurtosis, multiple values are being used. So let me just correct this. Fine. So when R is 0, this power is 0. So it's just going to be 1. So you're summing 1 n times. So n by n, that gives you 1, right? So that is okay. When R is 1, so now what is going to happen is you have some observations which are less than the mean. You have some observations which are greater than the mean, right? And so you are going to subtract. So let's say, maybe I'll just add a new slide here. And then we can discuss this. Really sorry for the confusion. I think I messed up something here. But yeah. So let's say these were your observations, 0, 1, 2, 3, 4, and your mu is actually equal to 2, right? So if you add them up, it's going to be 10 divided by 5 observations, so that's 2. So now your x minus x bar, that's going to be, this is going to be -2, -1, 0, +1, and +2. So if you sum this thing up, you're going to get 0, right? Another thing which you can do is you can calculate the square of this difference. Now, when you're doing a square, you get positive values, right? So you're going to get 4 and 1 and 0 and 1 and 4, right? All positive values. So in this case, the sum that you get, that's going to be a positive number. It's not going to be 0 anymore, right? So from what we saw here, so when the power is 1, when you're summing up this difference, so you had, this is what mean does, right? It's the central tendency. So you're going to have numbers which have a negative difference. You're going to have numbers which have a positive difference. And when you sum that up, you get 0. So 0 divided by n, that's going to give you 0. And then when R is actually equal to 2, as one of you rightly pointed out, when R is equal to 2, in that case, mu2 is going to be sigma square, right? This thing. And because when you're dividing 10 by your n, that's going to give you sigma square. That's the variance. This is the formula of how variance is defined. Okay. And when R is 2 and 3, and when it's 2 and 4, then these values of the central moment, they help you calculate the skewness and the kurtosis of the distribution, which we're going to see in the upcoming slides. Because the formula requires both of them, mu2 and mu3, and for kurtosis, it's mu2 and mu4. In the lecture videos, it was explicitly mentioned mu3 and mu4 only, but the formula demands mu2 also. So that's why I've just mentioned it here, right? Can you just confirm if it's all falling into place now? Yeah?
Yes, ma'am. Yes,
Yeah?
ma'am.
Okay. All right. Thank you so much. Okay, fine. I will correct it in the slides before uploading it today. Fine. So just taking forward from that thing. So if A is that expectation value now, if it is indeed your mu, right? So don't get confused. Mu, x bar, expectation of x. For the time being, you can consider all of them to be the same thing. There are minor differences in each of them. I will briefly explain it to you I think in the next slide. But for now, you can consider all of them to be the mean or the average or the expectation. Same thing, right? So when you're defining A as the expectation, then the expectation of this function, right? X minus A to the power R. Again, that's going to be your central moment, R at central moment. Same thing from the previous slide. And like we just saw, when R is equal to 2, it's the second central moment is actually equal to variance. And one other form of writing this, so if you rearrange this thing, so it's like a square, a minus b whole square, right? So what it's going to be a square plus b square minus 2ab. So you open that. It's like a bracket function. So you apply expectation to each of these three parts, right? So expectation of x square, expectation of x square, and then expectation of 2xex product. again, which you can do an expectation of each of these things. So when you solve the whole thing, right, you are going to get it of this format where you do expectation of x square and the square of expectation of x and the difference between those, right? So this is another format of calculating the variance. Okay. Now, what are mean and variance doing exactly? So mean is sort of like the central tendency or the center or the middle of that probability distribution, right? The mean, especially in this case, it's going to be 1, right? And the variance is a measure of dispersion or how the data is concentrated around the mean, right? Is it very, very farther away from the mean, or is most of the data nearby the mean? Okay. So data which has a lower variance, you'll expect that, okay, that's a good value. You can trust that value. It's not too spread out. Of course, but it does depend on what sort of a data you're looking at. Sometimes you might be interested in looking at a higher variance, depending on whatever the problem statement is. But yeah. So a few extra things. So just like you can find, so it's like transformation. When you want to find expectation of x, it is a function of x, but these functions are not, you're not doing like a square or something of the random variable. You just have few additional constants. So now expectation of a constant, what value do you expect a constant to take? It's always going to take that constant, right? So the expectation of a constant is going to be a constant. On the other hand, what variance do you expect in a constant? Nothing, right? It will always be constant. The data is not going to be spread out here and there. So the variance is going to be 0. Now, when it's expectation of, you are multiplying your random variable with something and you're adding a constant to it. So think of this as, so let's say this is the kind of plot you're seeing. So by the way, this is a normal distribution. It's going to come up in the next week. Whenever I'm drawing something like this, can anybody think about what is it on the x and y axis? What am I drawing here? What do you think x and y axis here indicate? You can type it in the chat, or you can unmute yourselves and give it a go. You have seen plots like these, right? I just drew one of them a couple of slides back. So it's pretty much the same thing. Any guesses? Any of x or y axis? No, you don't want to try? Okay, no worries. So on the x-axis, I am looking at my random variable actually, right? It's going to be that random variable. On the y-axis, it can either be my, since let's say I'm drawing it like a continuous random variable, typically, because you can see it's all continuous. So it's going to be a continuous random variable. It can either be my probability density function, PDF, or it can also be frequency. Either way, it does not matter. If it's the probability density function, then the area is going to be 1, right? Because the area gives probability. But if it's frequency, so it's actually the exact occurrence at how frequently, in depending on how many data points you've taken, how many times you're getting this, right? So either way, now if you think about it, if I am multiplying this thing, if I'm multiplying it by a or something, so it's now this b here is going to shift my graph somewhere, right? If b is positive, it's going to get shifted to the right. If b is negative, it's going to get shifted to the left. And my expectation of x, so again, it's going to be, this expectation stays the same, but this a gets multiplied to that value, right? So this whole thing gets shifted. With a, it gets shifted like in terms of multiplication, and with that b constant, it just gets shifted left and right by that proportion, how many times, right? And when you're talking about variance, so shifting something left or right by a constant value, like linearly, when you're just adding b or subtracting b from it, it's not going to change the variance, right? Because the spread of the graph stays the same. It's going to get shifted left, right, but doesn't matter, right? The data is still as concentrated around the mean as it was before. On the other hand, when you're multiplying a value, the variance, the derivation can be checked separately, but the variance gets multiplied also. But it does so because if you remember, we do have some squared values here, right? So if you'll derive it, you can see that the variance gets multiplied to square of whatever constant you multiplied your random variable with. Okay. So this is how the format is. These small formulas, they will come in handy, and you can probably get some direct questions from these formulas. Okay. Now,
What is the sorry for
yeah,
the
no, no.
interruption, ma'am. What is the aim of doing this? I mean, what is by doing this means by multiplying the constant and adding. What does it mean? Means it get the graph more flattened, or the it showing the pickedness of the graph or something like this. Uh,
It
I'm not
will,
getting it.
okay, fine. So now, think about this x value here. So let's take some examples. Let's say the values were maybe something around 1, 2, 3, 4, 5, 6, 7. And let's say, so 4 was your mean. Okay. You have values from 1 to 7. It is a discrete random variable. Sorry, it's a continuous random variable, but I've just marked 7 points here. Let me change the color here, right? So let's say it's 1, 2, 3, 4, 5, 6, 7. From 1 to 7, and 4 is your mean here. Now, let's say if I'm defining my new function as x plus 3. This was x. Now I'm going to draw x plus 3. So it's going to be the same format, right? It's going to look the same thing. But now this is going to start from 4 and it's going to end at 10, and the mean is going to be at 7, right? Let's say this is what the format was. So now
Okay.
now I don't have a here. A is equal to 1 here. So what happened was, when you looked at the expectation, it was the original expectation plus b, whatever the shift was. The shift was of 3. So right, the mean did get shifted by 3. And the variance is not going to be affected, right? Because you see the plot looks exactly the same. It's the same shape. It's just shifted left or right on your axis. So that is what b is doing here. So b is appearing in the expectation, but b is not appearing in the variance. That's one thing. Now let's take another example. Let's say a is equal to 2. Okay. So now you see your point. So originally, so now what you're going to do is you're going to calculate 2x here basically, right? So the value at which it was the mean, now it's going to be 16, right? The minimum value is going to be 1. The maximum value is now going to be 49. And it is not going to look so symmetric anymore, right? You will have 25 here, you'll have 36 here, you'll have 4 here, you'll have 9 here. But you see, this is no longer, it's not going to be linear. These values are going to be closer to each other. These values are going to be much farther away. So if you draw them, it's going to look something like this, right? So now the expectation is also going to change, the central value, and the variance is definitely going to get changed because the shape has changed, right? Oh, why did I square it, by the way? Sorry, I'm so sorry. Let me redo it. Wait, let me redraw this. So we're doubling it, right? So now your values are 8, maximum is going to be 14, here it's going to be 2 and 4 and 6 and 10 and 12. So let's say it's linear, it's still linear. it is still going to be the same shape, right? So it is still going to be like this bell curve, right? This was also normal. This was also normal. But now you see, earlier this thing was what? It was, the range was 6. Now the range is 12. So it's spread out. The data has now spread out, right? If you want to draw it in the same thing, your original one probably looked something like this. It was much thinner. Now it's spread out. Let's say the area is still going to be 1, right? Because we are doing a probability distribution function. But it's now spread out, so the variance has changed. The mean has also changed. Obviously, the mean is now 8. So it's going to be A multiplied by the original mean, so 2 multiplied by 8. And it's spread out. And the amount by which it's spread out is going to be square of 2. So it's going to be 4 times the original variance. Because it's spread out here.
Variance is high here.
Variance is
Variance is
high here. Yes,
okay,
yes.
okay.
Because you see this range here. Earlier you drew between 1 and 7. Now you're drawing between 2 and 12. So it's almost double the range. Earlier this was the plot. Now the plot is spread out. It's a thicker bell, a wider bell, right? So the
Okay,
variance
got
has
it.
increased. Yeah. All right. Now, there are two terms which come very frequently when you're talking about statistics. These terms will be introduced in greater detail in the upcoming lectures. But the two terms are probability and sample, population and sample. So, we had vaguely discussed this in the last week in the session, if you were here. So, population is everything, right? What you originally what on whom your statistics are actually going to be applied, right? Let's say when you're talking about some disease spread, you are interested in the population of a particular place, but it's not possible to test everybody, right? You're testing a small proportion, maybe 5% of the people only, or whatever. So that small group that you select, which you consider that they are going to represent your population, that is group is known as the sample. Right now, both your sample and your population. So in an ideal world, you will have data of the population, but you don't have that, right? But we often say that population mean, population variance. So here it's not written, but population mean, that's represented as mu, and sample mean, it's represented as x bar. Okay. Likewise, population variance is represented as sigma square, and the sample's variance is represented as S square. And standard deviation is nothing but the square root of these values. So that's going to be sigma and S respectively. So now, as of now, we are using these terms interchangeably. So let's stick with that for now. As and when the difference emerges, we will talk about them in more detail. One thing which did come up in one of the lectures was using some sort of a denominator here. So if you remember this calculation we did, right? So what we're doing here is we are calculating x minus x bar, right? Typically, x bar is used to denote the sample. But let's say what we're doing is from each of the observations, these original observations, we are subtracting the mean, we are squaring it up, and we are dividing it by a certain value. So here we divided it by 5. So n is equal to 5. So what you do is when you're dividing x minus x square by n, this is mainly for the population. Ideally, you should have written mu here, but let's say we're talking about mean. So observation minus mean whole square, when you're dividing it by n, you take population. And when you are dividing it by n minus 1, this is for sample. Now, the rationale behind this is, so, okay, before that, can you tell me which of the two values is going to be greater? Simple maths question. Which of the two values is going to be greater? Which denominator is smaller? Denominator being smaller gives you a greater.
First one.
First one is going to be
Bigger one.
no. So this is n minus 1, right? So when you're dividing something by a smaller number, then you get a greater value, right?
Oh, sorry.
Yeah. So
Okay.
yeah, it's okay. I just wanted to confuse you, right? So which means, so this is variance. Both of these are variance. This is your population variance. This is your sample variance. Sorry, S square, right? So now this means that sample variance, which we denote as S square, that's going to be greater than your population variance, which we denote as sigma square. Now, the reason to do that is, so in an ideal world where you had the population with you, you actually knew what the variance there was. Let's say you were able to find out some parameter for like 10 million people and you calculated that. Now you took a sample of 100 people from there, you calculate the variance there. Ideally, those 100 represent those 10 million people, but normally they would not, right? It's not going to be a perfect representation. So the variance you calculated is not actually going to be perfect, but you want it to give you a better indication of the population. So you add a certain extra value to it. So you actually add up some value, you increase it so that you are accounting for the unaccounted variance. You were not able to capture the whole variance, so you purposefully add some variance to it. So that's the rationale. This correction has a name to it. I am forgetting that name. Not relevant, but somebody's name correction, something like that. Whoever gave this formula, right? So this is what the concept was, which was talked about in the lecture. For the time being, it's not so important because we are not making a distinction at the moment between population and sample, but it's just good to keep this in mind. All right. So this is what there is. So the variance of the population it's 1 by n. So n is the denominator. I mean, just the sentence framing is a bit off. It's n as the denominator and the variance of sample as n minus 1 as the denominator. All right. And when you're talking about standard deviation, so here variance, it's a square number. So it's always going to be a positive value. When you're taking the square root, you can always, obviously, square root can be both positive and negative, but by convention, standard deviation is also denoted as the positive value. And so standard deviation, these are just some housekeeping notes of sorts. Standard deviation will have the same unit as your data, but variance will have a unit which is square of the original unit, right? So just keep these things in mind. They're not absolutely essential for understanding the rest of the lectures. Okay, so now that we'll now slowly move into talking about different kinds of distributions. So two major things that one can do about distributions is to look at the shape and the size of these distributions. So again, we have not explicitly talked about the normal distribution. It's going to come next week, week 6. But imagine this is like a perfect plot, right? It's a symmetric curve where the center, somewhere in the center, it's the highest frequency or the highest probability of this value occurring. And as you go away from the mean, the probability of these values coming as the outcome decreases uniformly, right? So this is a normal distribution. It's also called the bell curve. Now, for such a distribution, there are these three terms, mean, median, and mode. So again, mean is what we've been talking about. Median is the value which is sort of the middle of these values. So if you arrange your observations in an increasing or a decreasing order, the center value that comes up, that's the median. And mode is the value which is the most frequent value. So naturally, from this sort of a curve, you can see that all three of them are going to be the same value. But you can have curves which look a bit different. They may be skewed. So the word skew means shifted here and there. So they may be shifted a little left or right. And in that case, your mean median mode, they would look something like this. So the easiest way to see the mode here, mode is always going to be the highest peak, right? Because you see here it's frequency, it's the same thing. The PDF or the frequency, it's just the unit is different, or the area under the curve is different, but the shape of the graph stays the same. So the highest, wherever the highest part of the graph is, corresponding to that, the value on the X, that's going to be your mode always. Mean is basically, yeah, it's going to be, because yeah, I mean, mean is a little shifted. We can always calculate that. And mean it is mostly between mean and mode. So now you can have these two plots shifted, where it's shifted. The nomenclature is done based on where the tail is. So tail is like the lowest frequency thing, right? So when the tail is on the left, you say it's negatively skewed. When the tail, like here, it is on the right, you call it positively skewed. So these plots, so to understand, so this normal distribution, this is sort of a reference, okay? And you can calculate two coefficients here. One is called as beta 1, and a similar value is called gamma 1, right? So beta 1 is this, when you're talking about these central moments, so it's the square of the third central moment divided by the cube of the second central moment, right? So this is that format. Again, it's given for discrete values here. So xi minus x, when you're doing a whole square, that becomes your second central moment. This is your third central moment. And then you're doing the respective powers. And you can find the square root of it. And that becomes beta, that becomes gamma 1, right? It's just, these are two very similar quantities. Again, you can calculate one from the other. Now, gamma 1, as per convention, since it can have a sign, so positive sign for a positive skew, negative sign for a negative skew, that is just going to give you a better picture, right? If you're interested in the direction. If you're not interested in the direction, then reporting beta is a better option. And as we're going to see in the demo from R also, so R calculates gamma 1 here, right? So it will give you a sign along with it for any distribution. So that's okay. The other way you can judge a graph is based on its height. So, so there are two alternate sort of opposite meaning words, peakedness and flatness, right? Peakedness is how, what the peak is like. So it's higher peak or lower peak. And flatness is like, is it flat or is it not flat? So these are opposite terms. So kurtosis is the more formal term for it. So when it is the normal distribution as indicated by the red curve here, the middle one. It's called mesokurtic. When it's a higher plot, it's called leptokurtic. When it has a lower height, it's called platykurtic. You don't exactly need to remember these names. And now the coefficient for that one is going to be the fourth central moment divided by the square of the second central moment. And a related value here is actually gamma 2, which is 3 less than beta 2. And gamma 2 again is a better sort of metric to judge, because then what happens is if it's less than 0, then you can say it's lower than the normal distribution, so it's platykurtic. When gamma 2 is greater than 0, you can say it's leptokurtic, right? So greater than 0 and less than 0 are the things you're looking for here. And but when you have beta, you are actually looking at greater than 3 and minus and less than 3 values for beta 2, right? I hope I did not confuse you. Please ask questions in case anything is not clear. Okay. Okay. So the next topic that was discussed is quantiles. So basically, you can divide your data into as many parts. But when you're dividing it, so you have a data, you can draw as many lines. Each line, what it is indicating is the probability of observing a value to its left and to its right. So typically, value to its left is p or it's alpha, and to its right is going to be 1 minus p or 1 minus alpha. It's the same term, right? So that's quantiles with an n. And depending on if you are how many parts you are dividing your data into, if you're dividing it into 4 parts, you say it's quartiles, which is one of the most commonly used. So actually all of them are very often used, dividing into 4 parts, dividing into 10 parts, or dividing it into 100 parts, right? So the values that P or alpha will take, it's 0.25, 0.5, 0.75, and of course 0 and 1, right? P and alpha can always take values 0 and 1. Other than that, it's going to be 25%, 50%, 75%. For deciles, it's going to be 10, 20, 30%. And percentiles is going to be each of these from 0 to 100, right? So that's how quantiles are divided. For percentiles, typically you would have heard percentiles when you're talking about ranks of people, right, in competitive exams. Quartiles are very often used. I don't think we will have time today to discuss this in any more detail, but quartiles are typically used when you're making something that's called as a box plot. Okay. I think it's going to come up in one of the lectures. If not, I'll anyway discuss that. So that's where and deciles, it's also used when you're interested in groups of 10% each. Okay. And so one more concept which is there, it's sort of like an estimate. So when you know the mean of a certain distribution, when you know the variance of that distribution, and when you're looking at some values about the mean, right? A few values to the left, a few values to the right. So let me just draw something here. So again, I'm taking the example of the normal distribution. So this is your mean. And let's say this is C here, right? So this is mu minus C. This is going to be mu plus C here. So maybe you are interested in this thing. Or the other option is, again, same thing, mu here, mu minus C, and mu plus C, and you're going to draw this. Maybe you're interested in this parts, right? Can any of you match these with this? Which is which? Which equation indicates what? One is left. Are you sure? See that again. I'm just trying to confuse you, but see that again. So one is actually the right one. Because you see the difference of, so what observations are you interested in? Those which differ from the mean by a value greater than C. So an observation, let's say this one, it differs from mu by a difference which is greater than C, right? Yeah. So this one is this, and this one is this, right? So depending on what sort of a question is asked, you can use either of the formats, right? So you just want to get a lower or a higher estimate that when you're interested in this shaded region or these shaded regions, what is the minimum or maximum probability by which you will observe values in the shaded region. But these are typically lower estimates. So let's say if you are actually to calculate, so here I've given you the example of a normal distribution, but it's applicable to any distribution, right? which is why it is not a very good estimate. It's okay when you don't know what sort of a distribution it is, but when you know what the distribution is, you can actually calculate the area of the shaded regions and you will get that probability. Right? So, but when you don't know the distribution, but you do know the mean and the variance, you can get an estimate that at least these values are at most. So, when you're using this format, it's going to give you a at least sort of a form, right? And when you're using this thing, it's going to give you an at most sort of form because this sign, right? So the probability is less than this value or the probability is greater than this value. That's the format we are looking at. So range, no, you don't get the range. You get the higher or the lower estimate. Because here you see this is greater than C. So it's these things. So when you're talking about this shaded region, the area of the shaded region is at most going to be variance of x by c square. It's going to be less than this. And when you're talking about this shaded region, it's going to be at least 1 minus this area. But it can be much higher and it can be much lower. Range, you can always say the highest range is going to be 1, the lowest range is always going to be 0. But we are not typically interested in these values, right? Did I understand your question correctly? Let me know if I've not understood it correctly, if you want to clarify something else. Okay. Missed it. Okay, so what I mean to say is these values, they are not giving you ranges, they are giving you an upper bound or a lower bound. In case 2 here, this one, it's giving you a lower bound that the probability is at least going to be this value. And in this case, it's going to give you an upper bound that it's maximum this value. So the area of the two left and right regions, it's maximum something. And the area of this middle region, it's minimum something. That is all you get. You don't get ranges here by Chebyshev's theorem. Right? All right. Okay. So finally, there were these two distributions of random variable that was also talked about. So over the next week, we are going to talk about more distributions, but we are starting off with two discrete random variable distributions. One is degenerate and the other is uniform. So degenerate random variable means that it will have a certain value. I don't know why this minus sign came out. Yeah. So this one pretty much means that at a certain value, you're going to have a probability. It's only going to be that value. When it's anything less or more, it is not going to have any probability. So a random variable can only take one value. It's almost as if it's a constant, right? So the mean is C and the variance is 0. It's like a constant. So you can just remember it as a constant here. And CDF, so if you remember the cumulative distribution function, it's the probability until that value. So until it was C, so it was not C, it was less than C, you got 0. And as soon as you got C, you had the probability 1. So even if it's anything higher, the probability still stays 1. Right? And uniform distribution is this simple thing here. You have your random variable. This is your uniform distribution. The whole area that you're talking about, this area is obviously equal to 1. Also, although we are talking about discrete variables here, but this is what it's indicating, right? So that is all. And I've just taken screenshots from the slides that were shown in the lectures. So this is a function in R where which is RD unif. So the syntax is the first value is how many observations do you want? And then this is like the maximum and minimum values between which you want to pick out. So you want 10 observations, you do that multiple times, you're going to have different mean and variance, right? Theoretically, you would see that the mean should be 50.5, the variance of a uniform distribution should be 833, but you will see sometimes it's very close, sometimes it's farther away. But as we have seen in one of the initial lectures, when you increase n, you get probabilities which are much more closer to what you would expect. This is how probabilities are defined, right? When n is a very high value. So when you increased n, mostly now you've got probabilities which are very close to the actual expected. I mean, the mean you get is very close to the expected mean. And the variance here also is very close to the expected variance. So again, just to say it again, here in this case, think of these theoretical mean and variance to be your population mean and variance, right? The mu and the sigma square. And the ones that you get here in these samples, they're going to be x bar and s square. So when you have a smaller pop sample, it doesn't really represent your population that well. But when you have sample sizes larger, your population is represented better. So this is the funda in statistics, that a higher sample size is always better, but it's not always possible, right? You can't always, whatever you want to talk about, taking some sample from people, you want to make some observations. It's not always possible to make 10,000 observations or 10 million observations. You can have multiple samples, that is also true. But again, you can probably have 5 times you can have 100 samples. So the effective sample size still says 500. But of course, you can have multiple samples, and you can calculate mean and variances of all of them independently or all of them collectively. But at the end of the day, it all boils down to how many samples you had, how many like individual sample size, the effective sample size, how much did you have? Okay, good questions, all good questions. All right. So with that, we come to an end to the discussion of this week. Now we have some practice questions. So any real case example for z-generate probability where entire probability is 1? Any constant. Let's say, let me think about it. So let's say something works only at a particular voltage, right? So when the voltage is, let's say it's 220 volts, only then it's going to work. If it's anything less or anything more, it will not work. Something like that. It's a funny example, but something like that. So the probability, so the value that that function can take, it's only x. It's only x can occur. So when x occurred, so CDF is the collective of that, right? Until that value, from minus infinity or from whatever value you can accept, until that value, what is the total probability? And yeah, it's like until there, right? I'll think of a better example, but yeah, right now it's that. Okay, so for these practice questions, it'll be nice if you can have a pen and paper with you, or at least try to understand how it's done. Like you can try to give pointers on how to solve it, how to go about it, and I can just solve it with you. Okay, so let's say there's a continuous random variable x, which is denoting the voltage measured in an electric circuit in volts. Let's say the range is between 0 and 20 volts. So assume the probability function. So again, here we're talking about a continuous random variable, but the probability that you see here, it's 1 by 20 for when it's between 0 and 20, and it's 0 otherwise. What is the value of mean and variance of 2x? So would anybody like to tell how do we go about it? Because solving these questions is not very difficult. It's more important to understand how do you think we should go about it? What should we start?
By expectation of mean, we get the mean. Means the integration formula of
Yep, of
expectation of
expectation.
mean. Yes.
Perfect. Right? So the formula for expectation of x, that is equal to x fx dx. And so typically it's going to be from minus infinity to infinity. This is the formula. But now you know that from minus infinity to 0, it's basically 0, right? And then from 0 to 20, it makes sense. So fx here is actually 1 by 20 dx. And then from 20 to infinity, it's again 0,
0. Yes.
right? So this is how we are going to go with it. So 1 by 20 is a constant. It comes out of the integration. So we are doing an x dx, that the formula is x squared by 2. And then you're going to fit in these values 0 and 20. So you get 1 by 20 into, this is going to be 400 by 2. Second 20, 20 by 2, that's 10. Right? So expectation of x is 10. Now, the other thing you can also do, you can calculate the variance of x. Now, variance of x, if you remember this formula, it's expectation of x square minus expectation of x whole square. So you need to do the same thing, but now instead of x, once you calculate this thing, right? So expectation of x square, that's going to be from 0 to 20, x square 1 by 2, 1 by 20, this thing, right? I'm just replacing this one here by x square because everything else is 0. Now 1 by 20 comes here. You're going to have x cubed by 3 from 0 to 20. It's going to be 20 into 20 into 20 divided by 20 into 3. Oh, 3 stays here. This one. That's going to be 400 by 3. Okay? Something around 130 something. Okay? It's going to be close to, let's say, 133 something.
100
Now,
by 3. Yes.
say that again.
100 by 3.
What is 100 by 3? What did I miss?
Uh,
Why is it 100 by 3? Does it have to be 100 by 3? 1 by 20 is here. Calculating x square, x cubed by 3. Let me see. Wait. It's 133 variance. No? Oh, wait. It should be 100 by 3. What did I miss? Can anybody identify? 20 is here. X square. Oh. This is
right.
130 something. And then you can calculate the variance, right? So that's going to be so when you calculate the variance, that's going to be this 400 by 3 minus 10 square, right? So that's 400 by 3 minus, that's going to be like 100. So that's going to be 300. It's going to be 100 by 3. So variance comes out to be 100 by 3, right? Variance of x from this formula, right? And now when you want to find the mean and variance, we are going to use the same thing, right? A is equal to 2 in this case. So the mean is going to be twice of the original mean. So that's 20. And variance is going to be 4 times of this thing. So that's going to be 400 by 3. That's okay, right? We are on the right track, right?
Okay.
Yeah. So the first thing, we calculate the mean of x. We calculate the variance of x by this formula. So we already have ex here. We're going to square that up. So that's going to be 10 square. We calculated expectation of x square here. which was 400 by 3. So we got EX and we got variance of X. Then we knew those formulas of transformation where mean of double of a random variable is going to give you double of the mean, and variance of double is going to give you 4 times the original variance. It was exactly the same graphs that we saw, right? So we just multiplied by those values and we got it. You can also try, just for like a sanity check, you can directly do an expectation of 2x here, right? Obviously, for variance, it's going to be slightly more, like you'll have to do a couple of more steps, but you can do that, right? Instead of doing it this way, let's say your x was directly 2x. So you calculate, so instead of x here, you fit 2x, instead of this x also, you fit 2x, you calculate both the squares, and then you get these expectation and variance, you should still get the same answer. Okay? You will get the same answer. So it's just going to be like a double check that either of the methods you follow, you'll get this right answer. Okay. All right. Okay. So now let the continuous random variable denote current measured in a thin copper wire in milliamperes. Suppose the range is between 0 and 20 milliamperes, and assume that the probability distribution function is it's again 0.05 and it's between 0 and 20. What is the CDF? Now, just a hint, it's the same question. Here, the probability distribution first function was written as 1 by 20. Here, it's written as 0.05. Still the same thing, right? So what is the CDF? Anybody? Any guesses? Sorry. So again, CDF is probability until that value, right? So first of all, let's say we are going to define minus infinity to 0, and then it's 0 to 20, and then it's greater than 20 until infinity. These are the 3 ranges we can define this in. So probability is only present here, right? It's only some values here that give you probability. Anything below this was 0. Until 0, there was no chance something was happening. Now, all observations were between 0 and 20. So after 20, you have already gotten all your observations. So anything more than 20 will still give you the total probability. That's what CDF is doing, right? Cumulative distribution function. Total probability until that value, for all values until then. Right? Now for this one, so I don't know if I would be able to derive this thing, but so the probability, let's say this was 0, this was 20. Let's just call it minus infinity and infinity. So the probability distribution function, which is, right, PDF, it was something like this, right? Right? And this whole area is equal to 1. Now, when you talk about CDF, it's basically successively showing up these areas, right? So let's say when A is equal, X is equal to 1, you're looking at this area here. This whole area is what is going to give you. Then when you're looking at, let's say X is equal to 10, you're looking at this whole chunk, right? So these respective probabilities, this is actually going to be, so this is 0.05, right? So this area here is 0.05 into 1. This is 0.05 into 10, and so on, right? So that is what CDF here is going to be. It's going to be 0.05 into X. Does this make sense? Yeah. Okay. Good. Good. All right. Fine. Why did I do these plots here? Okay. Consider an experiment of tossing three unbiased coins, right? Let X denote the number of heads. What is the variance of X? So again, the first thing you begin with is when you have cases like these, so you're going to have a discrete variable here. So your uh, sample space, right? So you can have, uh, so again, you're going to have these 8 observations here, right? 2 into 2 into 2 for these. And X is the number of heads. So the values that X can take is going to be 0 heads, 1 heads, 2 heads, 3 and 4 heads, right? So now when you want to, what is happening? Just give me a second. Something got stuck. Um, okay. No, you cannot see my screen right now. Share screen. Yeah, it will not be 4. Sorry. You can see the screen now, right? So yeah, so it's not going to be this one. It's just 0, 1, 2, and 3. Yeah, okay. So would any of you like to say how we're going to solve this? Any guesses? What is happening? Okay, while the time I'm figuring out what's wrong with my computer, can any of you just, would you like to try how we can solve this? It's a simple question. Okay. 1 by 8. Yeah, that's right. Okay, so we are going to calculate each of the probabilities here, right? Right? So again, simple thing, you have this formula variance of X, right? That's going to be expectation of X square minus expectation of X whole square. So for each of these probabilities, so probability when X is equal to 0, X is equal to 1. So it's a discrete random variable, right? So as you've been mentioning correctly here, right? So if you see how many cases there are going to be, it's going to be 1 by 8. This is going to be 3 by 8, 3 by 8, and 1 by 8 here, right? Out of 8 cases. When you want to calculate the expectation of X, it's going to be 0 into 1 by 8 plus 1 into 3 by 8 plus 2 into 3 by 8 plus 3 into 1 by 8. And then expectation of X square. Probability stays the same. Instead of X, you're going to write X square. So it's going to be 0 square, then 1 square, then 2 square, And finally, square, right? So this one's going to give you 3 by 8 plus 6 by 8 plus 3 by 8. That's going to be 12 by 8. And this is going to give you 3 by 8 plus 12 by 8 plus 9 by 8. So that's equal to 24 by 8, right? So again, for variance of x, calculate this. You're going to get the answer, right? I do have the answer written here. So it's going to be, yeah, so this is basically 3, right? So it's 3 minus this 4 by 2 whole square. Yep, sorry. 3 by 2 whole square. So that's 1.5 whole square, right? It makes sense, right? It's just formula based. Okay. Now for this question, so the question, it can be any set of values. So in this case, it's the time taken to reach a temperature of 50 degrees Celsius for some 100 wires for different materials, and the data is stored in some vector. Now, when you do have a data like this, you can calculate some values. So before we go into R, I would just like to give you a quick demo of some functions that were discussed in this week, and then we'll sort of just move into this question here, right? So let's say you are given a population. I'm calling it pop1 again. So we are not discussing R in this course very frequently. It's often in some lectures in a week, or it's not always every week. So if it's a relatively newer concept for you to use R or R Studio, I would just recommend you to not lose touch with it, because if you don't use it for a while, you can forget it. Okay. So we are not going to, we will not be doing something very complicated here, but basic things like what does this sign mean? This is an assignment operator. Anything on the right side is assigned to the left side. Whenever you see this curved bracket, it indicates you're doing a function. It's called a function in R. It's going to take an input. It's going to give you an output, right? So mostly that is what we are doing all throughout today's discussion. So the function C is used to define the vector. You're using that, you're defining population 1. I'm pressing Control Enter or Command Enter, and then you can see here in the global environment, you have your variable pop1. It is a vector, numerical vector of 10 values, and these are the 10 values. So you can calculate the variance. A simple formula is the function here is VAR, var. You do that, you get the variance. Again, it was the same thing, that what it is doing is it's actually calculating a sample variance. So it's dividing it by n minus 1. If instead you want to divide that thing by n, it's simple maths that the denominator was n minus 1. So what you do is you multiply it by n minus 1, and then you actually divide it by n. So that's what I'm doing here, right? If you do that, you're going to get a population variance. And just like we discussed, sample variance is slightly larger than population variance. So the original thing that was calculated was 8.98. But now when you consider it to be a population, it's now a smaller value. And then, of course, standard deviation is the square root of variance. Now, whether you do it for the population variance or you do it for the sample variance, whatever it is, you can just use the function sqrt, and whatever you enter, you're going to get the standard deviation for that, right? Likewise, now here you see the difference. It's almost roughly one value. So it was almost 9, this is almost 8. So it was a larger difference, right? Because you really have a very small population. But when the population size is large, so I'm selecting all of it and running it at the same time. So population 2, you can see it has slightly more observations. It has 30 observations. So when you do these two, this bar out here, it was 10.4. The new variance, which is your population variance, that's 10 point, it's a little over 10. So now you see the difference has actually reduced. So when you have a larger sample size, it doesn't matter, right? So when n is 10, n minus 1 is 9. So like dividing something by 10 and something by 9 will make a larger difference. But when you have something, say 100, and you're dividing it by 100 or you're dividing it by 99, it's not going to make a lot of difference. It's going to stay pretty much similar. So that's exactly what I just wanted to show here. So you're using the function var. Now this var function is directly available in R. Okay, you did not have to install anything specifically or anything specially for this. But when we talk about moments, so the idea behind something that you need to install some additional functions into R is that not everybody requires these functions, right? So until I'm going to teach this course, I have not calculated moments exactly for my data set. So I never had to have these functions in my computer. So what I can do, so if you're using if you're using RStudio, there are a few things you can do which just make it slightly more user-friendly. So you have this tab here, packages tab. So here it's alphabetically arranged how many packages you have installed on your computer. So I can go and search on M, and I will see that I don't have something which is with the name moments, right? So it's just not here. So I can install it. There is a way to install it here. It doesn't matter. It's better to learn it through command line. So the function to install set of functions is install.packages, everything in small quotes, bracket, and in double quotes, I write moments. So once I run this, for this, I need internet. This is the only step for which, oh, okay. Anyway, let me try something. It's okay. So I had it half installed initially, and I just removed it. So here it's said, what happened here? Yeah. So install.packages moments, it's installing, and it's installed. Yes, so for that you need to Google it. There's no other option. When you're searching, when you want to do something, very often you're going to read about it. Let's say you want to do a particular function, so you Google it up that what function in R allows me to calculate moments, and then one or the other page is going to tell you that this function belongs to the package moments. It's a very good question. Thank you for asking. Right? It's a very pertinent question. Right? So you installed moments. Now let me go and see if it shows here. I mean, you don't as such need to check it, but just to show it to you. So now you see moments is here, right? It gives a little description, it gives me the version, and that's it. But now you see there's a checkbox here, and it is not checked right now. So let's say I do know that all dot moments is a function from moments. So I run it. But here what it says is that error, I could not find the function, this one, but I just installed the package, right? So now, although the package is there on my computer and RStudio can see the case there, it's there somewhere. But again, in this session of RStudio that I've opened, in this session of R, I have not asked it to access these functions. It's there sitting somewhere, but I've not opened it. I've not called it, or I've not loaded it. So to load these functions, to load all the functions of a particular package, the command is library. So you either load a package or you say you load a library, it's the same thing. So once I run this, see what happens to this checkbox here. So when I run this, the checkbox gets ticked. And now I can run this one and it says all moments. So it's able to do it. Now it just gave me these three values. I am not sure what these three values indicate. So if you remember, there's this question mark functionality available. So when I do this, it's going to give me, this is known as a vignette of a function. So it gives me a very small description of what all things it can accept and what all parameters I can set. So typically it's going to give me two moments, 0, 1, 2, and it is Normally it's not going to give me the central moment, it's going to be the raw moment that's about 0 rather than about the mean. So these are the important parameters. So you got this. If you want to calculate the central moment instead, which is about the mean, you can specify central is equal to true. And if you want to get more central moments, you can say order is 4. So you get 0, 1, 2, 3, 4. All right. So this is what all moments function does. You can calculate skewness and kurtosis also. So again, skewness, it's directly giving you gamma 1. But when you do kurtosis, it gives you beta 2, not gamma 2. So if you remember, you can subtract 3 from this to get gamma 2. So it was 2.4. Now when you subtract 3, you'll get minus 0.6, right? And anything less than 0, it means the kurtosis is lower. So the distribution that you're looking at here, it's going to have a smaller peak than a normal distribution. But had it been a higher value, the peak would have been greater than a normal distribution, right? Makes sense? I'm sort of rushing through this because we just have half an hour left and we have last week's assignment also to discuss after completing some practice questions. So you can stop me at any time if something's not clear. Okay. Then you can also find out quantiles here. So when you don't specify anything, when you just say quantile, it is going to give you quartiles here, right? So 0, 25, 50, 75, and 100 percentages. Right? So what it's doing is that what was the value at these quantiles, right? So if you see population 2, it was these values somewhere between 1 and 13 or 0 and 13. Right? So it's going to give me what was the value, the least value, what was the highest value, and what was the value at these positions when you're arranging them in ascending or descending order. And again, if you just say probs is equal to 0.1, so it's 0.1 is nothing but 10%. So it's going to give you that percentile or that quantile. And instead, if you give it a vector, so if you remember, if I run this vector here, it's going to give me everything from 0 to 1 in intervals of 0.1. This is what the seek function does. So when instead of specifying just one value, if I give it this whole vector here, it's going to give me all of these corresponding quantiles, right? All deciles in this case. Just like we talked about the moments package, there's also the other package per with a triple R. And this is mainly for your function RD unif. Again, same thing, you need to install the package, then you would need to load the library. And once you've loaded, you can just do a double check if you want. It's not necessary. You will see your package here and you will see that it's loaded. And you can just run this thing. So the first argument here is how many observations you want. The next two arguments are the maximum and minimum. But whichever order you give it in, it does not matter. Higher minus higher and lower or lower and higher. This is a relatively old package. So it does say it was deprecated in something, but you can ignore that warning. And the last thing is you can make these plots. So if you remember, for population 2, if you want to visualize what the distribution actually looks like, you can do a table, right? The table function gives you the frequency distribution. So the value 0 was there 1 time, the value 1 was there 2 times, and so on. And then you can make a bar plot out of it, right? So these were the values, these were their corresponding frequencies. But sometimes instead of frequencies on the y-axis, you would want the probability, right? So in that case, probability is nothing but relative frequency. So in that case, this thing, so what we did initially was we did a table where for each of them you had the frequency, but now instead of frequency, you have the proportion or the probability, right? So it's the same thing, but as fractions now. So when you plot that, the nature of the graph will stay the same. So at 4, it's still going to be the highest peak. At 0, 2, 3, and 5, and 13, it's still going to be the lowest peak. But now your y-axis is going to change. So here the y-axis was frequency. But now you see the y-axis is actually now probability. So that's pretty much it. So the rationale to show you this was for this question. So when you want to find out the second and fourth raw moment, can you just tell me what function you're going to use? I'll just write it here. I'm not let's just try to wrap this up because we still have a few things to discuss. So what do you remember what function we are using here?
Mu rth.
Say that again. The name of the R function.
Mu r.
Mu R. It says mu R, but you remember the name of the function in R, like RStudio, language R. So it is all dot moments. So let's quickly try to show this. So this is my vector, right? So what I'm going to do here is, so let me define the vector as vec1. This one is the assignment symbol C, and I'm just sort of typing this whole thing in. It's a very long vector, so it's not coming in one line. Just to show it to you here, I'm just dividing it into different lines. Yeah, all right. So this is the vector. I'm going to run this thing here. So you can see vec1 is here. It's 100 values. Now, if I write all dot moments, vec1, so you see it give me the first 0, 1, 2 raw vector, raw moments. And I'm going to write, so for the question, it said, I want to find the second and fourth raw moment, right? So I'm going to do it like this. So this is the 0th raw moment, first raw moment, second, third, and fourth, right? So this is my second raw moment, and this is my fourth raw moment. So I got the value, right? Now, if I want to find the second and third central moment, can you tell me what changes I'm going to do to this thing? How do I find out the second central moment? Any guesses from here?
Central equals to true.
Perfect, right? So here, instead if I write central is equal to true, I don't exactly need the fourth one, but anyway. So here I get the second central moment, right? And this is the third central, right? Okay. Now, if you want to find coefficient of skewness and kurtosis, here for skewness, let's say the one which I get directly from R, that's gamma, and the one which I get for kurtosis is beta. So it's the respective name, right? Skewness bracket your vector, kurtosis bracket your vector, right? The one that we saw here, this one, right? It gives you gamma 1, kurtosis give you beta 2. You don't need to subtract anything from there. And if I want to find the third and sixth deciles of this data, what function am I going to use?
Quintile.
Quantile. Yep.
Oh,
So this
sorry.
one, and it's going to be of, let's say, of this format. So instead of pop2, I can write vec1. I can do this. So if I wanted, which one did it ask? Third and sixth deciles. So it's going to be this one and this one, right? 30% and 60%. So that's it, right? Okay, that's good. Um, okay, a very similar question. So falling marks out of 100 were given to 200 students. This time there are 200 observations. And the examination will declare that a candidate can be admitted only if the marks are in the top 30 percentile. So 5 candidates, they obtained the following marks. Candidate 1 had 73 marks, 65, 80, and 54 marks, and 5 had 36 marks. So which of these candidates are going to be admitted? Now, do not confuse 30 percentile with 30% of marks. So by the way, here it says top 30 percentile. So we are interested in 70 percentile, right? Up to there. You remember? That's how percentiles are divided. That's how percentiles are defined, right? So for this data, again, what we are going to do, we are going to read it into R. Now, just to clarify, questions like these would not come in your exam because you would not have access to R Studio there, right? But this is just for your practice, right? So I've read this data table. There are 200 observations, so it's all read correctly. Now I am going to use the function quantile. I'm going to say marks, and the probability that I'm interested in is only 70%, right? So let me write 0.7 at 70 percentile. So when I run this, it gives me 70.62. So that means people who have marks 70.62 or lesser, they will not be admitted, but anything beyond 70.62, they will be, right? So now see, this is good that here in this case, when you said 70 percentile, you got value, which is very close to 70, but that will not always happen. So don't confuse 70 marks out of 100 with 70 percentile, right? So this is greater than 70.62. This is greater than 70.62. So candidates 1 and 3 are going to be admitted. Okay. Okay.
Ma'am,
Suppose,
could
yeah.
you please repeat it?
Okay.
I
Sure, sure,
didn't
sure,
get
sure.
it.
So here it was asked that people out of 100, they have got these marks. There are 200 students in a class, and the examination says that a candidate will be admitted, they'll be qualifying for this exam if the marks are in the top 30 percentile, right? So when we define percentiles, we are mainly dividing our distribution in such a case that 70% of the people are going to be uh, below that thing, 30% of the people are going to be above that value. This is what percentile is indicating, right? So if you remember when we talked about quantiles, we said the probability of observing a value to the left and right. So what percentage of people? Quantile is going to divide the proportions, right? So, so when we talk about the top 30 percentile, we are basically interested in the 70th percentile from 0. That's how it's defined. It's defined from the left side onwards. So what we did here through the quantile function, we wanted to find out the mark of the student, who, not the mark of the student, but the marks within that distribution, below which there are 70% of the people and above which marks there are 30% people. This is what quantiles are doing. So at 70%, at that distinction, at the marks 70.62, 70% of the people, so which is 140 students, 140 students have marks less than 70.62, and 30% of the students, which is 62 students, they have marks more than 70.62. So the question here said that candidates will be there only if they are in the top 30 percentile, right?
Okay.
Right? So above 70.62, there were these two candidates, so they are going to be admitted.
Okay.
Okay. All right. So suppose it is known that number of items produced in a factory during a week is a random variable with mean 50, and the variance of the week is 25. So what can you say about the probability that the week's production will be between 40 and 60%, right? So again, you have the mean and the variance, and you're looking at an interval about the mean, right? So the mean here is 50, and the variance here is 25. And let's say whatever the distribution was, if this was the mean, this is the range you're looking at, right? So within. So the formula of Chebyshev's that we are going to look at is going to be this one, right? That it's less than, it's within C. So it's basically X minus mu less than C. This value is greater than 1 minus variance by C square. I think it was C square, right? Right? So fit in these values. It's 50, and you are interested in 40 to 60. So 50 minus 40 and 50, I mean, yeah, 50 minus 40 and 60 minus 50. So C becomes 10. You're looking at values 10 lesser or more than 50. So that's going to be 1 minus variance is 25. C square is going to be 100. So that's going to be 1 minus 1 by 4. That's going to be 3 by 4. Or that's 75%, or that's 0.75, whatever you want to say. So in terms of probability, you can say that the probability that this week's production is going to be between 40 and 60 is at least 75%. So it's a very high chance that your production is going to be 75%. It can be higher, it can be 80, 85, 90, 95%, but at least it is 75%. Okay.
Ma'am, how are we getting the value of C?
So this mu, you are sure, you know it's 50, right? Now for a distribution, this is mu, and they are saying that we are interested the production to be between 40 and 60. So here it's 40, here it's 60. This is what we are looking at. So if you see this notation, so X is your random variable. So any value minus mu should be within C. So any value minus mu, so let's say this value minus mu should be within 40 and 60. So how less than mu are you and how much greater than mu are you? You are there by 10,
Okay. Okay, got it.
right?
Okay.
Yeah. I think this is the last question. So a fair dice is rolled 100 times, and let's xi denote the outcome in the ith roll of the dice. Compute the variance of rolling it 100 times. Okay. So again, this is a slightly confusing question. So let me just show you. So basically what you're doing here. So if you remember, you have, so I don't think we explicitly talked about this, but you can also have variances of multiple random variables, right? And the variances get added up when you're talking about multiple random variables. So each of them is a random variable, right? So when you're rolling a dice once, you can calculate the variance. Again, the same thing, I think we just solved it, right? Your mu is going to be 3.5. Your variance is, you can calculate the variance by expectation of x square minus square of expectation of x. So that's going to give you 35 by 12. And the variance, when you add of each of them, it's just going to get added. So 35 by 12 into 100. So that's what it's going to be. I just write it here, right? Because we are sort of running out of time now, and I don't want to extend your time. It's 2 hours is a lot of time to pay attention to. So the assignment questions from us, like the 4th week's assignment, there were a lot of good questions, some difficult questions also in this assignment. Would you want me to rush through them right now, or can we discuss it maybe next week? Or are there any one or two particular questions that you would like me to discuss today? See, the solutions are all here. Most of them are quite explanatory. In case there is one or two of them that's not clear to you, you can let me know. Otherwise, next week or any other week, whenever you get time, whenever we get time in the course, whenever we finish it early, we can solve these questions. We can take a look at the solution then. I think that will be better, right? Because there's no point in rushing through it in like 5-10 minutes, right? The last question. Um, the question of the assignment or the one that we just saw right now? Oh, yeah, they're independent. That's correct. They're independent. Okay. So, I think it's better if we end the class today, right now. Okay. Because it was a lot of discussion, right? We will anyway get time in one of the upcoming classes. We can always, and if required at the end, after 12 weeks and before your exam, if in case we still have something missing, we can always have an extra session to cover up things that were not discussed. But yeah, so that's pretty much what all we had for today. The assignment deadline is going to be next Wednesday. And for the next week's session, we meet next Friday. That's 1st of March. Same time, same link. All right. So is there something you would like to discuss, or I think I'll just stop sharing my screen now. So yeah, thanks for joining in, everybody. It was a relatively longer class today, and hope all of this is improving our understanding of the course and you're liking it. We are almost halfway through. Next week we'll be halfway through the course. So if you do have any suggestions, I think just today or day before you got a link for the suggestions, for the feedback on these problem solving sessions. So if there's something, I mean, you can directly tell me or you can just write it in that survey. Anything works. All right. All right. I'll see you all next week then. Thank you for joining. Good night.
Hello.
Yeah.
Ma'am, I have to ask one question from the
Yeah.
multiple theorem of probability from the
Hmm.
lecture 18. If you have the time, I can ask.
Sure.
Ma'am,
Sure.
I uh, able to solve this question like it is in the lecture, it is explained by the uh, sir, but I
Mhm.
am not getting it. This is uh, how to compute the probability of each pile has exactly one ace, like this was the question in the lecture.
Okay. Fine. So what you can do is, on the discussion forum,
Hmm,
can you post this question? And
hmm,
either I or any of the other TAs, we
hmm.
can just re-explain it to you there. It'll just be, I think it's just going to be better that ways. You know how to
Okay,
ask a question on the discussion forum? There's a ask a
okay.
question thing,
Hmm,
right? So just
okay,
do it there. I think it's going to be more convenient.
okay.
Yeah. All right. Thanks. Okay, then. Good night, everybody. Bye bye.